Okay, 2.1 is talking about relations and functions, and we're going to talk about relations first because relations are general and functions get more specific as a special kind of relation. So, a relation. I'm just going to make up a kind of relation that I want to talk about. Let's say we relate things to their colors. So over here we'll have the things, and objects or things, and then over here we'll have the color. How about roses? Roses are red. Violets are blue. Sugar is white. And it kind of ruins the poem, but we're trying to do colors here. How about a fire truck? A fire truck is red. That's what I think of growing up. Fire trucks are red, but it seems like at some point in my life they started making yellow ones. Maybe it was before I was born, but it seems like some kind of terrible travesty that happened at some point in my life. They began to make yellow fire trucks rather than red fire trucks. And now you'll find both. You'll find red and yellow fire trucks. So that's a relation. That's an example of a relation. Now, the relations and functions eventually, and functions are we're going to deal with pretty much exclusively after this section. They relate and they perform functions on numbers. So, we could have, here I'll use a table this time. X and Y, an XY table. You've seen that before. We'll put in 1, we'll put in 3, and we'll put in 5. And 1 will be related to 2, 3 will be related to 7, and 5 will be related to -3, or whatever. Okay, so here's another relation. It relates 1 to 2. Technically, the technical term is called mapping. 1 is mapped to 2, 3 is mapped to 7, 5 is mapped to -3. Okay, and that word mapping comes up in this type of a diagram. It's called a mapping diagram. Okay, and this is called a table. And there's many ways, I'm sure, that there's 4 common ways that we can talk about relations and functions, and here they are. Okay, we did a mapping diagram up above. We did a table. You could also do a graph. You could do ordered pairs. You can see that all of these are 4 different examples, 4 different representations of the same relation. And actually, it's also a function. We'll talk about what a function is and what it is not in a minute. So whether I tell you that 1 is related to 2 by putting them together in parentheses with a comma between them, or by putting them across from each other in a table, or by putting a dot at x is 1 and y is 2, showing you that there's that relationship between 1 and 2. Or I draw a mapping diagram and just put all the inputs here and all the outputs there and just draw arrows to how they're related. Just 4 different ways to represent a relation. Just a little bit of history. There was a man named Descartes, and he suggested, well, look at all these other ones, all these other ways of representing a relation. They take up a lot of room, especially if you want to extend this out. If I want to keep going and write more ordered pairs, or fill in more of this table, or make these input and output groups or sets bigger, that's going to start taking up more room. But all I have to do with this graph is keep putting more points. Just keep adding points, adding points, adding points. And that just takes up less space. And when you're talking about information, taking up less space is always desirable. So Descartes, he suggested that we do that, and that's what we're going to do a lot of times. Typically we'll use these 3. We're really not going to use this one much, the mapping diagram, but we'll use graphs, tables, and ordered pairs a lot. Okay, so There you go. That's a relation, and 4 different ways to represent a relation. But let's talk about a function. And to talk about functions, I always love to use this analogy. The analogy of a factory. Because when you think of function, there's this, if I ask you to define what a function is, most often people would come up with some kind of definition like it does something. A function does something. It performs some task, and that's exactly right. A function just does something, and that's what a factory does. So that's why it's a good analogy for me. A factory performs a function, and what it does is it takes stuff, especially a production, a producing, manufacturing factory. It takes raw materials and turns them into stuff, okay? And just to make it simple, so that our stuff that comes out is just, it only takes one type of thing to make it. We're going to make it a table factory. Really easy to draw, and tables typically are made of wood. So this factory has input of wood and output of tables. Okay? And that is a function. It performs a function. The guys in here, the workers, know exactly what they're supposed to do when they get wood. They do exactly the same job every time and output a table. Okay? Now, that's a pretty simple thing. And that, if you can remember this picture, it's going to help you a lot to understand what a relation is, what a function is. The important things about functions and relations is, first, that they have input and output. Okay? And the set of all the inputs is called set of all inputs. Okay, so let's say all the different kinds of wood you could use, cherry and oak and pine and walnut and maple, and all these different kinds of woods that you could use is called the domain. Okay, and the outputs, all the different kinds of tables they would make, just tables that are made out of those kinds of wood. A set of all outputs is called the range. Okay? So it's really the biggest things you need to remember, but there's a special thing about a function. So far, this could describe just a relation, but a special kind of relation that we call a function, let's put that here, a function, for one, it has inputs and outputs. That's what this I/O means. If you see it on your calculator or computer, it means stuff's getting inputted and outputted in this place. So here there's inputs, like this wood, and there's outputs, like this table. But a very special thing, important thing about a function is that for every input, there is one and only one output. What could that mean? Oh my goodness. Let me show you real quick by going up to the top again. I'll show you something. For example, this is a function while this is not. Okay, remember what I said, that for every input, so these are the inputs over on the left. Those are the things that you put in that prompt you to find the output. You go from here to there, input, output. So for every input over here, it has one and only one output. Let's look. Roses have one output. Violets have one output, blue. Sugar has one output, white. Fire truck has 2 outputs, red and yellow. Okay, so that it causes a little confusion. If that was a factory, that would mean that you put something in there and the guys aren't sure what they're supposed to do. They're supposed to make the red. You give them all the materials for a fire truck. Are they supposed to make a red one or a yellow one? They're not sure. That's not a function. Okay. I could talk about that all day long, but you get bored. So that's not a function. A function has one and only one output for every input, but this guy here, 1 goes to 2, 3 goes to 7, 5 goes to -3. None of these goes to 2 different things. We could make it into not a function. We could take 5 again and send it to something different, send it to 0. Now it's not a function. Now it's just a relation. But if we just use the green ones, then it's a function. Okay. So that's what a function is. And in this section, we're going to use a specific kind of, no, let's back up a little bit. Specifically for graphs, let's talk about a graph. Let's talk about all these things and how we would notice that they're not functions. Let's just go through and make each of them not a function. Okay, so we need to make it so that an input has more than one output. Okay, so let's go with 1, and we'll make it go to 4. Okay, so we'll just add that in, and we'll represent that throughout all of these. So 1 goes to 4 now. So 1 goes to 2 and 1 goes to 4. That's going to be no good. That can't happen with functions. So we've made it not a function. So we take 1 and it goes to 4. Okay, so that's how we do it in a table. Let's jump over to the mapping diagram real quick. We would just have to extend this out, put a 4 here, and draw another arrow to 4. And there we go. Okay. Now on a graph, this is something called the vertical line test is going to come out of this. So 1 went to 2, and now it's also going to go to 4. Okay. So here's what happens with the graph. If it's not a function, if an input has more than one output, then what you're able to do is draw a vertical line and have it touch 2 points. If a vertical line can touch more than 1 point on a graph, you've shown that it's not a function. So that's called the vertical line test. So the vertical line test is one that tells you whether or not a graph is a function. If you can draw a vertical line, let's put this here. Vertical line test. I know you could state it several different ways, but I'll just put it into these words. If a vertical line crosses a graph at more than 1 point, then the graph does not represent a function. All right, there you go. That's one way to put it. And you see that if you have a graph, and we'll look at some example problems later, if you draw a vertical line and hit the graph at more than 1 point, it's not a function. Okay, and the last thing that I don't want you to get freaked out by is called function notation. So previously we would have seen a function or a formula or an equation, whatever you want to call it. It was like y equals 3x plus 1. Okay, now we're going to use a different notation. This could still be 3x plus 1, but instead of y, instead of having a table that would be x, y, and let's say we put in 1, then that would be 1 times 3, and that would be 3 plus 1 is 4. If we put in a 2, we'd get 7, and so on. Instead of x, y, it would be x and something else. We'd call it f of x. Okay. Otherwise, the table would look exactly the same. 1, 4, 2, 7. Something goes in and something comes out. This thing acts the same way as y does. Y equals 3x plus 1 is exactly the same thing as f of x equals 3x plus 1. The reason why we're moving to function notation is, let's now say we have g of x equals 2x minus 7, and s of t equals 4x minus 8, and q q of r equals 9x plus 3. I have all these different functions, and the reason why is, and stay with me for just a second here, if all of these were y's, it's y equals, y equals, y equals, y equals, then say I was standing way over here, and I wanted to draw your attention to one of these functions. If these were just y's, and I said, hey, look at that function over there, and I wanted to actually look at this one, if it was just a y over here, you wouldn't know which one to look at. I couldn't just point at it. I'm too far away for you to tell what I'm pointing at. So I'd have to say, look at that y function, that's 2x minus 7. A much easier thing to do if I'm standing over here is say, look at the function g. This is the only one that's called g. So that's what this g is. The g, let's use black here. The g here is the name of the function. So g is the name. X, that's what we call the input. All right? And g of x, that's called the output. Okay, y used to be the output, now g of x is the output, or f of x is the output, or q of r is the output. So s is the name of this function, and t is the input. Q is the name of this function, r is its input. And actually, this should be a t. Now the t is the input, and this should be an r. Excuse me. So that's the way it should have been. This is t, this is r. If this is s of t, you better have a t over here, because that's the variable that you need to plug stuff into. Okay? So that's function notation, and we will use it and get used to it as time goes on. Okay, thanks for watching.